Hello, bonjour, hola, guten tag, ni hao, and namaste. I'm Winnie, the event coordinator with the Petroleum Institute for Continuing Education, commonly known as PEACE, and I'm looking after the technical support aspects of today's webinar. Our agenda today will be introductions, our PowerPoint presentation. At the end of the presentation, there'll be time for Q&A, and then we'll have closing remarks. I'd like to firstly welcome everyone to start our webinar in a few minutes, and please type in the chat pod on the bottom right-hand corner any audio issues you may have. You should clearly hear my voice right now. Please ensure all browsers are closed and speakers are turned up. I'd like to start with a few introductory words about PEACE and RPS, who are running today's webinar. RPS is a global consultancy offering a wide range of consulting, advisory, and operational support services to the oil and gas industry. PEACE is one of the two training companies owned by RPS. The other is Nautilus World, and between us, we offer a wide portfolio of classroom courses and online webinars to the upstream, midstream, and downstream sectors of the petroleum industry. Thank you for joining us today. Please refrain from asking questions until the very end of the webinar, and they will be addressed at the end. The questions that you have can be typed in the bottom right-hand corner in the chat box. If the webinar runs longer than a half an hour, we understand if you need to leave. The webinar has been recorded, and a recording link will be sent to all participants at the end of today's webinar. Our instructor today is Dr. Taiba Bash. As an ocean engineer and an expertise in modeling tsunami and other coastal hazards, Dr. Bakash has extensive experience with a wide range of numerical models of ocean processes, including ADCIRC, ROMS, FunWave, and NewWave. We will now start our webinar. Taiba, please take it from here.
Thank you, Winnie. Okay. Hello, everyone. Good morning, good afternoon, good evening, wherever and in any time zone you are. Thanks for joining us for this webinar. My name is Tayyebe Tajallibakhsh. I'm an ocean engineer and tsunami scientist at RPS ASA in Rhode Island, and I'll be giving this webinar on coastal inundation, focusing on tsunami hazard. I've worked on different tsunami hazard assessment both within the US and internationally, including a number of nuclear power plants. And in this webinar, I'll talk about coastal inundation, especially related to tsunamis. We will discuss the need for risk assessments when building facilities along the coast to assist decision makers, planners, business owners, and insurers. Excuse me for a second. Okay, good, thank you. Okay. And I'll be answering the questions at the end if we have time. If not, I'll be happy to answer your questions through emails. Okay. What's coastal inundation? No, they stopped it. Thank you. Okay, sorry. Okay. What's coastal inundation? Obviously, it is ocean water where it's not supposed to be, or where it is expected to be normally dry land. So what are the sources of coastal inundation? How often does flooding happen? How significant can the flooding be? There are four main causes of coastal inundation. The most frequent one is flooding due to astronomically high tide in low-lying area. These are regular events related to a spring nip cycle. So they occur a couple of times per year, and they can result in water level that are in order of magnitude of a meter higher than high tides under nip conditions. And this produces minor flooding pretty frequently along the coast. And if in future we see the sea level rise, it will become more problematic. Classic example of it is Venice in Italy and also Miami in Florida. Another abnormal rise of water is generated by a storm in order of magnitude of meters, which can cause extreme flooding in coastal areas, particularly when a storm surge coincides with normal high tide, resulting in storm tides reaching up to 20 feet or more in some cases. And of course, it can happen in seasonal basis. For example, we can remember Hurricane Sandy, for the east coast of the US in New Jersey specifically, or Typhoon Haiyan in Philippines in 2013, which resulted in economic losses about $14 billion, mostly due to a storm surge. The next source is tsunami. Tsunami is a sudden displacement of large body of water which makes a wall of water fast moving on shore. It can't be prevented, can't be predicted. It is very rapid and random, but could be mitigated. In average, every 2-3 years we had a tsunami since 1900. And in a specific event like 2011 Tohoku earthquake and tsunami, the estimated losses were more than $300 billion. As I said, it is pretty rare and very random, but when they happen, they have large amplitude and it's more severe and catastrophic than any other of the coastal flooding. The last case we are talking about is sea level rise. Actually, this one is kind of different from the other sources because when we talk about flood, people think of, yeah, water comes on land and then it goes back to the ocean. But for this case, water comes in land and it doesn't go anywhere. It just stays. Sea level rise is happening now and it is expected to continue for centuries and likely will accelerate. And its effects are visible in long term, like next decades. The rise in sea level is linked to some primary factors included in global climate change as well, like thermal expansion and melting of glaciers and polar ice caps. Global sea level rise was about 17 centimeters, which is about 6.7 inches in the last century. However, the rate in the last decade is nearly double that of the last century. And the recent study says we can expect the ocean to rise between 2.5 and 6.5 feet, which is equal to 0.8 and 2 meters by 2100, which is enough actually to swamp many of cities along the US East Coast like NYC. Imagine if we include the Greenland ice sheet meltdown, sea level rise would be about 23 feet, which is 7 meters, and it is enough to submerge London. Okay, why should we care about it? If you live in coastal area like we do in Rhode Island, and you have infrastructures or business in this area, you are in the risk of flood. Well, we should consider the population growth in the coastal areas increases the risk of coastal hazard as well. And if we look at the numbers, we had average global flood losses in 2005, which was estimated to be about $6 billion per year, and it will be increasing to $52 billion per year by 2050. And it is not including the climate change. If no mitigation steps are taken for climate change, coastal flooding could cause damage about $1 trillion annually by the year 2050, which is actually jaw-dropping. Okay. These are the causes of coastal inundation. Can we do anything about it? Yes, of course we can do something about it. We should use this information. We know what kind of risk we have. We have done risk assessments, and we should implement some technical and financial resources for both short-term plans and long-term plans. Like emergency response when we have a storm coming and we decide to put sandbags or barriers or evacuate the coastal area. Also, we should have long-term plan to reduce the risk from coastal hazards. The FEMA estimates that for every $1 spent on mitigation, about $4 is saved. There are different options for long-term planning, like hardening the coastal structures, changing the land use, elevating coastal area, and making seawalls. Soft adaptation, like nourishing natural systems like mangroves. Actually, mangroves and wetlands are often considered to provide significant protection against the storm waves and tsunamis and shoreline erosion because they are able to dissipate wave energy. in future webinars, we will talk more in details about other coastal hazards and flood from other sources, but today we are going to focus on tsunami. Okay. Actually, tsunami is a timely topic. They have been in the news quite a bit recently. Like this week, we have the 5th anniversary of Tohoku tsunami on March 11th, which happened due to a magnitude 9 earthquake, and about 16,000 people are reported as dead, and more than 2,500 people were missing. Also, there was a tsunami warning last week in eastern Indian Ocean because of a 7.8 magnitude earthquake off Indonesia, which actually we were lucky that didn't happen or didn't attack any shoreline. Okay, what is tsunami? Tsunami is a series of ocean waves that are produced by sudden displacement of large volume of water, just like dropping a rock in a pond. This is in contrast to typical ocean waves, which are produced by wind stress on the surface of the ocean. If you look at these diagrams, we have shown the different sources of the waves on top, their period on the bottom, and on the vertical axis, you can see the total energy of them in the ocean. Tsunamis are between tides and wind-driven waves in the period between a couple of minutes to a couple of hours, and they have different sources from seismic activities to sometimes meteorological sources. And the maximum total energy that you can see in the ocean is through wind-driven waves, which is actually not surprising because they can be generated everywhere on the water. Okay, let's look at the tsunami evolution. Tsunami life can be divided into 3 different phases. The first one is generation by any force that disturbs the water column, such as earthquake, movement along a fault, which reshapes the sea surface into tsunami, then propagation from deep water to near shore in shallow coastal area. Then we have inundation. The amplitude of the tsunami wave may be very small in deep water, less than a foot, which is about 30 centimeters, which is relative to the wavelength of the wave, and water depth is very small and might not be noticed by sailors in deep water. The deeper the water and the longer the wave, the faster the tsunami. Actually, it can travel as fast as a commercial jet with about 800 kilometers per hour speed. When it gets close to shoreline, a couple of processes happen. The first one is refraction. The wave speed is a function of water depth. So when it gets closer to shoreline, the bumps on the seafloor can shift the wave's direction, and the front tends to line parallel to the shoreline, like if you're around an island. And each individual wave must slow down too because the water depth is decreasing. And so you have a squeeze of the energy of the wave in a smaller volume of water. Then the wave height increases too. And you might have that a foot wave on deep water as 100 feet on shore. Most of the tsunamis cause the sea rise not more than 10 feet, which is about 3 meters. In the Indian Ocean tsunami event, we had waves as high as 30 feet, which is 9 meters actually, which is kind of scary. And then you have the flood into land, which could be 1,000 feet. Okay, what are the causes of tsunami? There are 3 main causes of tsunami that I can talk about. The one that gets most of the attention and historically has caused most of the damage is earthquake. Earthquakes occur when rocks on either side of the fault. Look at that figure. Move relative to each other and push the water, and the generated wave starts propagating in both directions. Not all the earthquake generate the tsunami waves. To generate it, we need a big fault and vertical motion of the fault. And typically, an earthquake bigger than 7.5 is needed to generate the big amplitude of the wave as a tsunami. Another source of tsunami could be landslide, like underwater mass failure or collapse of volcanic calderas. Landslide can generate wave by sudden displacement of water caused by a slope failure or by a collapse. Most of the time they are on continental slope near the shoreline, so there is very low amount of time for warning. And they are pretty fast decaying, so they have just local run-ups. The last source that I'm going to talk about is generated by atmospheric disturbances rather than seismic origin. In general, these tsunami waves are caused by traveling air pressure disturbances, including those associated with atmospheric gravity waves, pressure jumps, frontal passages, which normally generate ocean waves in open ocean and amplify them near the coast through a specific resonance mechanism, specifically in an inlet with certain resonance properties. They are not typically as catastrophic as seismically induced tsunamis, but are more frequent and happen in more places because the atmospheric disturbances, of course, can happen everywhere, and they are the source of them. Here you can see a case from January in 2016 for Florida. You see that the wave elevation is almost doubled because of this event. We had another one in New Jersey in 2013. It was in June. And then in Japan, it has happened in 1979, which actually killed 3 people because of the amplification in a harbor. Okay, let's look at this map. It shows historical tsunami sources, their causes and their effects. Like you can see the volcanic activities with triangles and earthquakes with circles, and the red shows that they had lots of damage, and when you go to white, they have almost little or no damage. You can see that Pacific Ocean by far is the most active tsunami zone, and we have about almost 90% of the earthquake in this area. But it doesn't mean that the other places didn't have any activity. You can see the Mediterranean, Caribbean, and Indian Ocean. All of them have been active. And in average, as I said earlier, we had every 2-3 years since 1900, we had a major tsunami, or like Cascadia subduction zone. There are studies which show that there is 37% chance of their activities during next 50 years. And here you can see what will happen if a tsunami attacks a shoreline. It is Indonesia in 2004. Actually, lots of people died because they went to the ocean when the wave retreated, and they went to see the bottom of the ocean, and they were not aware that this event shows that a killing wave is coming, and they will wash them away. Here you see that most of the structures are gone by the wave, and they will be part of the debris that tsunami gets and attack with them as a weapon, use them to attack the structures behind them. What can we do about it? Well, yeah, we cannot really do much in terms of acute response. There is warning system, but it is just to let us know that we should run away, and they need planning ahead of time. So you need to be ready for them and have plans way earlier. They are not like tsunami, like storms that in a couple of days you know that they are coming and put the barriers or sandbags. And you need to use some information like warning system and have land use structural hardening, design seawalls or tsunami platforms that have the first floor as just piles that tsunami wave passes through. And the best way actually to quantify the risk and make these plans work is through modeling. In the next slide, we will talk about how we should do the modeling and what do we need for them. Finally, actually, I should mention that another way of mitigating is having regulation for your coastline. Like in the US, we have regulations for nuclear power plants, which asks us to have detailed assessment for probable maximum tsunami hazard. And we should have a set of candidates of tsunami generated by possible sources and simulate the worst hazard on our coastline. And it should be actually, as it is very related to the geometry and bathymetry and topography of the area, it should be on a very high resolution. Okay, modeling. What do we need when we want to do modeling? First of all, you should have a good input data. They are very important in the modeling accuracy. We call it garbage in, garbage out problem. First, you should decide which kind of source you have, if it is a seismic, if it is submarine mass failure, and what kind of resolution you want to use. The higher, the better. And then you will use this as input to generate the wave using semi-empirical models or really solving time varying generation, and then propagation and inundation to have some outputs like time of arrival of the first wave or maximum current speed in different areas or maximum wave height and inundation map. Here, after this, we will look at a couple of modeling case studies to see how is the modeling process. And we will start with tsunami of Japan. This model, like this case actually, because of there are lots of information and data after that could be used as validation for your model if you are going to have a modeling. It happened on March 11th with a magnitude 9 earthquake. You can see the source on the map, and here you see the wave passing through the seawalls on land. We know that Japan is kind of country which is earthquake savvy, and it is recognized to have very heavily hazard mitigating programs. But after this event, they had about total damage from earthquake and tsunami together estimated to be about $300 billion. And the waves were about 39 meters above sea level in some areas, and they went inland up to 10 kilometers in Sendai, which is the closest major city to the center of the earthquake. Then it ended up actually caused the cooling system failure for Fukushima power plant and meltdown and release of about 300 tons of radioactive. Here we are looking at the model grids. You need, as I said, you need different resolution to solve your problem for your modeling. Here we have a 1 kilometer, 250 meter resolution and 4-minute grid for transoceanic simulation to see the effect on Hawaii and west coast of the US. This earthquake actually lasted about 3 to 4 minutes, and it was close to shore. Then the maximum value of the bottom of the ocean was simulated to generate the wave as a gradual time-dependent variable. Not for every case you can do the same thing because we don't have most of the time information for that. Most of the time we use just simple rectangular plane, but in this case we had the information, so we used it. Then we compared our output with the measured buoy and GPS and DART buoy data. So the red one shows the model and the black one shows the buoy. And you see that they match pretty well. We look at the time that the model predict and the elevation of the wave, which are good. The other thing that we compared was run-up. Run-up is shown in red here, is maximum elevation of wetted land, and inundation height in blue, which is maximum wave elevation at shoreline. We see that they are well predicted in the region. If there is some discrepancy, it is because of the complexity of the bathymetry and topography in this part of the region that we didn't have better and higher resolution data to use. So we see that our model is working and doing a good job. Let's use it for another case, like a prehistoric landslide. We know that about 33% of the US East Coast continental slope is covered by landslide scars and deposits. We had major historical events like Grand Banks in 1929 and Currituck, which was about 24 to 50,000 years ago. And it is the largest identified slide along the US East Coast. But there are some other scars that have been reported, like in Gulf of Mexico. For the East Coast, we have some in New England, and for the West Coast, we have some in the southern part of California. Here you see that we reconstructed the submarine mass failure geometry and kinematics, and we did the simulation. You see that the wave propagates to the deep ocean in the right, way faster than to the shoreline, which is something that we expect because the wave velocity is a function of depth. And here you see that we use different grid with different resolution, 500 meters, 125, and 32 meters. Again, as I said, we need high resolution to be able to do the simulation correctly. And as some output, we looked at the maximum surface elevation at this area. Actually, you see 125 meter grid and 32 meter grid. It shows that in Virginia Beach, we have the waves of 5 meter overtopping and passing to the coastline, and then they got refracted and got to the Norfolk with 2-3 meters surface elevation. Then we looked at the transect, this black line here, to see how is the wave changing when propagating to west. So here you see different time in minutes. Over the shelf we had 7 meter wave, and at the mouth of Chesapeake Bay we have about 3 meters wave height. So again, I'm saying that we needed a very high resolution to be able to do this simulation. Okay, let's summarize it. We said tsunamis are pretty rare, but when they occur, they are dangerous, more dangerous than we thought. They are more frequent and they happen in wider geographic region than generally appreciated. Their inundation is very extreme, but can be mitigated. Planning is the best approach to mitigate it, and to have planning, we need modeling of the inundation to understand the risk and be able to manage it. The first thing that you can do is having some knowledge of the history of tsunami in your area, which is a good indicator of what is likely to happen in a future tsunami event. If you have an oil refinery on the coastline, or you have power plant, or you are in government and you are thinking about your people on the shore in the coastal area, you should plan ahead and think of coastal structures to support your investment, your people, and your business. Okay. Thank you for your time. Here it is my email address, tayyebe.tajallibakhsh@rpsgroup.com. I would be more than happy to answer your questions or discuss any technical details if you are looking for. And I think, but we have a couple of minutes to answer a couple of questions.
That was wonderful, Tayyebe. Thank you so much. And as mentioned, please feel free to put any questions that you have directly into the chat pod on the bottom right-hand corner of the screen. Any questions you have, right into the chat pod. We'll take a few minutes for some Q&As with Tayyebe. Thank you.
Thank you, Winnie.
And it looks like we've got multiple people that are typing. Thank you.
Okay.
Tayyebe, I'm not sure if you see the question, but there is one question from a guest. Have you incorporated land substance in the model?
Okay. First, I should say that our generation model is separate from our propagation and runoff model. So we simulate first the generation of the wave, then pass it as a nest, as a boundary condition or initial condition on top to our propagation model, depending on where the source is and which kind of source we have. Then we have Manning factor as a function of space. You can play with that. If you have very high resolution data, you can even actually see the interaction of the wave with the structures and buildings on shore. Did I answer your question?
And there's another question from Ning Li. What are the vital factors for accuracy modeling tsunami inundation?
Both having good information about generation of the wave and very high resolution, I would say, topography and bathymetry data. Because as you saw, when you're getting the wave on shore, it will be refracted and reflected from the structures. So it is very important to have good information as input for your model. Any other question?
Well, people have an opportunity to think of any additional questions. This webinar is recorded, so we'll be sending out the recording link to all participants. And I do apologize if there was still music playing throughout the webinar. It looked like most of the people didn't have issues with music, but for the one individual that there was music, so I do apologize. That was hopefully in conflict. But when you do receive the recording link, it'll be a clean recording link for you. We also have a short evaluation that'll be sent out for all participants, so please take a few moments. There's only 5 questions to our evaluations, and we appreciate your feedback. If you could take a few moments to do that, that'd be wonderful. Thank you. I'm not sure if we'll allow just a few more minutes for questions for Tayyebe, and if anybody is interested in future webinars, there's a listing of webinars on our website, and you can go directly to www.peace.com for any future webinars, and we'll take a few moments in case there's any additional questions. But thank you all for your participation, and I hope you all learned and enjoyed the information that was shared from Tayyebe. Well, it looks like there might not be any other questions, so we will say adieu, and thank you all for your participation today, and I hope you enjoyed and learned something from our webinar. Thank you very much for joining us.
Thank you. Have a good day.